Okay, so that's yeah, that's basic like logistic stuff. Just look here, just look for this stuff. I think I can't remember if I said this to you guys or not, but it helps to reload the page. Sometimes I've gone to these and seen like old versions and I had to reload. Even I had to like reload twice once for it to like come up with the stuff I'd posted. So just to make sure you're seeing. But this is everything for this week, and then I'll start posting stuff for next week. Okay, sounds good. All right, and then if we go back to here today, so what are we doing today? Well, I posted, there's a handout here that I don't think I'm gonna have you work through in groups. I think it's probably better as like a whole class discussion, but I wrote the handout, so it's a nice framing device. So I think I will, I think I'll have us kind of talk through this. If I do end up being more lecture-y, it's 85 minutes is a long time. I might give us a break in the middle for like a few minutes. And then we can come back. So let me just, it's not going to open automatically. Can I make this open? Always open with System Viewer. Okay, that's good. Open. Okay, so all right, so let's get into the meat of what we're going to talk about today. So I want to just kind of today that I wanted to just sort of go over the Riemann sum idea, get back into it a little bit. Maybe write some stuff down kind of like abstractly, just to get us back in the mindset of abstract summation notation stuff. And it's also going to be helpful. We're going to be talking about numerical integration. So we're going to be looking at some other rules besides like left sum and right sum. There's something called the trapezoid sum. There's something called the midpoint sum. And we're actually going to be looking at a lab where we sort of see how good some of those estimates are for approximating areas in the curves. So I just want to go through some reminders here. So I guess if somebody is watching this later, I would just say pull up. I don't think I want to keep sharing the screen. So pull up this handout because I want to just be able to view the chalkboard. Okay, so let's see if we remember. And I might have you guys do some stuff in your seats for a few minutes, like rather than go divide up into groups. Oh, I didn't bring my good chalk. It's very upsetting. Oh well, it's down the hall. I can get it later. Okay, so do you remember summation notation? Let's have a reminder. Let's see. So as an example, I think that for that first one I said, what is that, I squared from 3 to 7? So that says. So an example. So there's I squared, I equals 3 to 7. So you would say something here like this is the sum of I squared from I equals 3 to I equals 7. I was going to read that in words. That's what I would probably say it in words. And all it means is like you just plug in, this is where you start, this is where you end. This I is called the index. And it's basically saying like, okay, I'm going to plug in 3. So I'm going to get 3 squared. And then I'm going to plug in 4. And then put a plus sign, plug in 4, put a plus sign, plug in 5, put a plus sign, plug in 6, put a plus sign, plug in 7, and then stop. So that's what the notation means. Does that seem familiar to people? Okay, good. So that's what the notation means. You can sort of start and stop anywhere, sometimes if it's convenient, although the increment's always by 1. So if I wanted like 3.5 squared, 4.5 squared, I could do something different. And I'll talk about that. We'll see that it'll come up naturally in Riemann sums, but let's just do another example quickly. That's one, say 3 over 2k plus 1. Right, the index doesn't have to be the letter I, it could be whatever letter you want. Where does that stop? 4? But you're always going to increment by 1. So now I'm going to plug in. I mean, you can do this purely formally, and we're going to see how to make Mathematica, how to make computers do this to calculate things for us. So sort of by definition, I'm just doing this. I'm just plugging all the values of k in that are relevant, right? This is about as long as I want to actually. Just at the edge of getting super bored. Okay. Did I do that right? Does that make sense? Could have typos somewhere. Tell me if you see typos. And then you can like simplify this. I don't really care what this sum is. It equals something, but I'm not gonna bother to do it. I'm just saying it equals some number. Same thing here. You could say, what is that? -3 plus 3 plus 3/2 plus, no, 3/3. Am I doing this right? Plus 3/5. So there's a little bit of a pattern here. Certainly there's a pattern because it's given as a summation. Is that good? Okay, so what about 2 and 3? I think those are interesting. I think maybe if you guys want to just like look at 2 and 3 and work in your seats and talk to the people near you, like turn towards someone near you and chat it out and try to go backwards, go from something like this and write it in summation notation. So like 2, right, is a sum starting with 16. And there's multiple answers, there's multiple possible answers, but why don't I give you guys a few minutes to work on 2 and 3 and try to talk to each other, make friends with people around you, say hi. Everyone say hi to someone near you. Say, hey guys, what about this summation problem, huh? You guys want to talk about it? You guys all should say exactly what I just know. But yeah, take a look, try it, see if you can get there somewhere. There are multiple answers, but remember that you have to increment the index by 1. So I can't just say like I can't tell it's about to skip 4 without doing something in the expression. That was vague, but I'll let you guys think about it. Ooh, I'm gonna get my good chalk while you guys are working on it. Hello. Once you come up with a plausible answer, you can always check it by writing out what you wrote down equals, right?
So it's something plus six. Where six behind the plastic bags. Something plus six. When the first one,
How's it going over here? Like that. Yeah, I like that. Other one's harder. Hi, I'm just gonna hover over you and oh. Oh, interesting. Those are weird fractions, right? I think you might want to just try to like find the pattern in the numerators and then the pattern in the denominators. Maybe I'll give you guys another couple minutes number 3, but what about number 2? Let's talk about number 2 for a minute first. What did people come up with for this? Yeah.
So our group came up with, okay, I don't know if I'm butchering this, but 96, so E would be E, and then 96, and then for the index, I was just whatever variable equals
12?
and then A plus 4, and then
Okay, that's interesting.
I feel like wrong.
What if you start writing this out? What do you get? So, put a question mark here. So,
Oh,
I plug in 12.
you bring up a good point there.
Right, if you try 13, it works for the first 2 seconds. Yeah, so that's gonna actually be 16 plus 17 plus 18 plus.
Yeah.
So that'd be all the numbers from 16 to 100.
Okay.
So I like it. I like that. It's interesting to try things and see what doesn't work. Okay, so no. 16 plus 17. Okay, what else? What other people try? Yeah. 12 plus 4i. So when you plug in 1, you get 12 plus 4 times 1. 12 plus 4 times 2 plus up to 12 plus 4 times 22. And so that does 16. 12 plus 8 is 20. And so on up to 100. 4 times 22 is 88. Okay, so that works. Other? That's interesting. So right, so you kind of force it to start at I equals 1, which is something that some people like to do for, just always make it start at 1. But you said, let's just start at 4. Make our lives easier, right? Good, so I like that. So that's just 4 times 4 plus 4 times 5 plus 4 times 6 and so on up to 4 times 25. And I think that does work. 16 plus 20 plus 24. Good, so there's definitely different answers. Like this works, sorry, Good try. No, I really appreciate it's interesting to see why things don't work more than why they do. Yeah, did anybody come with anything different? Everybody got one of those? Okay, yeah, I mean, sometimes if you're looking at this and you want to think like, these are all multiples of 4, and then you would say, okay, well, what is it? It's 4 times 4, this is 4 times 5, this is 4 times 6, up and so on, up to this is 4 times 25. And that's telling you something about, and you can see the incrementing of the 4, 5, 6. And then it's just a matter of whether you want to start at 1 or start at 4. There's actually an interesting idea called re-indexing that lets you like just change the index to start. I mean, I could force it to start at I equals negative 73 if I wanted to. That would be strange, but some people like things to start at I equals 0. So you could do 16 plus 4i, starting with I equals 0. So there's something interesting here that tells you you have to sort of figure out how many terms there are in the sum. That's kind of nice because you can immediately tell there's 22 terms in the sum, which is not as obvious just looking at it here. And even here, you have to be kind of careful, right? Because it's like 4 through 25 inclusive. 25 minus 4 is 21, but you have to add 1. Right, if you want to count the numbers like 3 through 7 inclusive, there's 3, 4, 5, 6, 7. So it's 7 minus 3 plus 1. If you remember that. So different things going on there. Someone else had some comment? Thought someone had their hand up at some point. Sorry. Yeah.
Oh, I was just gonna ask if there's like any plan for like the indexes for numbers.
Some computer scientist type people like to start at 0 always. Everything should start being numbered from 0. But from the mathematical point of view, I think it's nice to just start whatever gives you the simplest expression. Okay, maybe take another couple minutes on number 3 if you haven't gotten it yet. I'll give you another minute or 2 to talk it through. And if you finish 3, you can look at 4 and 5. It's groaning. Notice this one I don't have stopping, it just says plus dot dot dot. It's already a little bit different. If I was mean, I would have just written plus 1 here. Instead of 25 over 25. $36. One way to figure out if you know the pattern is what is the next term? What's the next numerator? 37. 49. So if I leave this as 25, I could write this as 1 over 1, I suppose. Okay, so do people know? So the numerator, I think, is, yeah. Go ahead.
We did 6i minus 5.
So the sum 6i minus 5.
Over I squared.
So it's funny, it goes plus dot dot dot. So it doesn't actually tell you where to stop. You're right, I guess on there it's like there's 6 terms. But in some ways, you could write infinity up here just to say, tell you to never stop. We'll definitely be talking about infinite sums later in the semester. But this means never stop, never stopping. Is that the name of that movie? Andy Samberg movie? You guys don't know this movie I'm talking about? Okay. It's a funny movie. You should check it out. Okay. So let's see. Does this work? So if you plug in 1, so just by definition, it's sort of something like this. And the numerator here is 1 over 1 squared, or 1 over 1. 12 minus 5 is 7 over 4. It's looking good. 13 over 9. It's looking good, right? Yeah, so what's the pattern that you noticed in the numerator, basically? The first thing you noticed? Like in the numerator. It's going up by 6. Yeah, and this is kind of the way to encode things that are going up by 6 is like, sometimes it's called an arithmetic progression. It's just it's multiples of 6, but maybe shifted by a certain amount. Then how many people immediately recognize the bottom as squares? Some of you did. Many people definitely did not immediately recognize the bottom as squares. It's good. It's definitely not. You sort of start to train yourself to look for these patterns, but I mean, there's interesting things going on. Did anybody not recognize them as squares and notice anything interesting? That was kind of a random question. Did anybody not notice they were squares immediately, but notice some other pattern that?
They start like the first one goes up by 5, and then it's 5 plus 2, and then it's 5 plus 2 plus 2, and then they usually add 2 each time.
Wait, at the bottom?
Yeah, I think so.
Oh, you're saying, okay, this goes up by 3.
Oh yeah.
And this goes up by 3 plus 2. And this goes up by 3 plus 2 plus 2. Oh, that's interesting. So, okay, so I just say this goes up by 3, by 5, by 7, by 9, by 11, by 13. So it's actually an interesting pattern in the perfect squares that they differ by odd numbers, successive odd numbers. Actually, you can sort of prove that by just expanding out n plus 1 squared minus n squared. Because n plus 1 squared is n squared plus 2n plus 1 minus n squared. Those cancel and you get 2n plus 1. So that's a nice pattern in the perfect squares that they increase by successive odd numbers. So that's something to look for. In fact, if I had used slightly different numbers, like if I'd added 2, I could have made this a little uglier by adding like 2 to every denominator. Like 3, 6, 11, 18, 27, much less recognizable. But if you take the differences, and again, notice that they're successive odds and you know it has something to do with perfect squares, then you might notice that each number is 2 more than a perfect square, you know. So there's just interesting pattern recognition things. That's good. Did anybody come with a different answer for this? Everyone did the same thing. I mean, I suppose you could start at 0 if you wanted to force it to, because the numerator seems to want to be 6i plus 1, like 1 more than multiples of 6. But then you would have to do what to the bottom? Yeah, Pinto. You'd have to do I plus 1. Yeah, there's interesting things you can do here, by the way. I didn't say this, but sometimes when you look for these patterns, it's actually something we'll do much more later this semester. But you can sort of say, okay, what if I just want to label, like just put the index up here? Like say I want to start at 1. Then this would be the index of each term. And then like things you start to notice is like, oh, 2 squared is 4, 3 squared is 9, 4 squared is 16. You know, you can start to see patterns that way. And then maybe you look at the numerators, you can also get the 6i minus 5 pattern. Okay, good. All right, so I'm Convinced we know summation notation. Okay. Excellent. Any questions about anything so far? Just please jump in. This number 4, it's just a property of summations that I think is sort of not worth mentioning. So I claim these are both the same. But I think if you write it out, you'll really see it. So like, if I wrote out, what was that, 1 to 5, 7i plus 4i cubed. What I wrote, yeah. So one thing you can do is you can really write this out. You know, you see me doing this already. I don't actually care what these numbers turn out to be. I more care about the pattern. So I'm not even evaluating this, even though it's just 11 or whatever, right? Plus 7 times 2 plus 4 times 2 cubed plus 7 times 3 plus 4 times 3 cubed plus 7 times 4 plus 4 times 4 cubed. And I got bored, so I'm going to turn this into a 4. So I don't have to write the 5th term. Now, when I see something like this, I actually feels to me like you can sort of rearrange things. Like I could rearrange the terms. There's all these terms that have 7 times, 7 times, 7 times, right? So that's the same thing as 7 times 1 plus 7 times 2 plus 7 times 3 plus 7 times 4 plus 4 times 1 cubed plus 4 times 2 cubed plus 4 times 3 cubed plus 4 times 4 cubed, right? Again, evaluating this, actually figuring these numbers out doesn't really help you. That's 7 times 1 plus 2 plus 3 plus 4 plus 4 times 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. And so that really is 7 times the sum. So it's really kind of like the distributive law, just with more than 2 things. Right, so you can really, I guess what I'm trying to claim is you can break up summations over plus signs and you can factor out constants. It's just a sum of sums. Oh, by the way, somebody said the big E thing, it's a capital Greek sigma. So sigma for sum. So, you know, it's a point, it could come up later if you actually try to evaluate some complicated sums, it can be useful to rearrange these things. But it's not that important. What about number 5 here? This is slightly a curiosity, but I think it's kind of a nice one. Has anybody ever seen this? If you, sometimes when you do these inline, it puts the I equals 1 to n there in this math typesetting language, but it's the same thing. So, has anybody ever seen, if you try to add up the numbers 1 through n, like bowling pins, 1, 2, 3, 4. How many bowling pins are there when you're bowling? I think you know the answer. Does anybody ever play bowled before? How many bowling pins are there? 10, yeah, right, 10 pin. So 1 plus 2 plus 3 plus 4 is 10. 1 plus 2 plus 3 is 6. There's a variant of Sudoku called Kakuro that involves sums of different digits. So you start to learn like 1 plus 2 plus 3, you learn 6, 10, 15, 21, 28, 36, 45, like 1 through 9 adds up to 45. Let's see. Here's a curiosity. I mean, it comes up in interesting ways. There's a famous story about the great mathematician Gauss that when he was a child, he was misbehaving in school, and his teacher said, go into the corner and add up the numbers 1 through 100, and don't come back till you have the answer. Thinking that would get rid of him for a while, right? So but then Gauss came back like a minute later with the answer. I think you know. Yeah, look at this. So I'm sorry, I really should start learning people's names. Are you Evan? I was gonna say Evan, okay. If you, what is this sum? Well, if you group the first and the last, that adds up to 101, right? And then if you group 2 and 99, what does that up to? And 3 and 98. And in the middle here, you have 50 plus 51, which adds up to 101. So how many copies of 101 do I have? Someone said it. 50. You have 50 copies of 101, right? So this is the same thing as 50 copies of 101. So that answer is 50 times 101, which is 50, 50. 5,050. There you go. That's how you add up the numbers 1 through 100. Very quickly. In general, there's another way to look at this. I mean, you could try to play the same game, although if you're an odd number of numbers, there's a weird like lone one in the middle you have to worry about. Although I guess you could just add the next number and then take it off at the end or something. But another way is to do something like this, is to draw boxes. Like, let's just say I wanted to add up 1 plus 2 plus 3 plus 4 plus 5. Well, this makes this nice little staircase pattern. Like this, right? And there's this thing you can do where I can make another, imagine duplicating this and flipping it over. That's faster than drawing each individual box. Do you see that? Like 2 copies of, so this is like 2 copies of 1 plus 2 plus 3 plus 4 plus 5 equals, well, you get this rectangle, and height is 5 and the width is 6. So that equals 5 times 6. And there you go. So that means 1 plus 2 plus 3 plus 4 plus 5 equals 5 times 6 over 2, which is 15. We just added 1 plus 2 plus 3 plus 4 plus 5 without ever adding, which is kind of a neat trick. And this works in general. This generalizes. I wish this was Notability, but I could just move this down here. Not used to it. On the iPad, you can just move stuff around. Let me just move some of these. So if we want to generalize, I just think this is nice and something everyone should know. So if we had the sum of I from 1 to n, right? So that's 1 plus 2 plus 3 plus dot 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 plus n minus 1 plus n. You could make a similar staircase. I feel like there should be dot dot dots in here or something. Oh my God, this is terrible. This is n, this is n. But then if I make another copy of it upside down, I mean, I'm kind of drawing the same thing I just drew, but I'm trying to think of this in more abstractly. Right, this is n. And so what's this? This is n plus 1, right? And so what we get is that 2 times the sum equals n times n plus 1. And so in fact, that means that the sum equals n times n plus 1 over 2. Oh, I actually did pause the share. I was worried I was sharing that screen the whole time, and on the Zoom, nobody was seeing the Blackboard. Okay, so yeah, so this is a nice formula. It's like, you could have used this. You could have also done 100 times 101 divided by 2. Would give you the same answer. Okay. None of this has had anything to do with Riemann sums yet. But this kind of fun, it's kind of fun stuff. Again, some of this will come back to later in the semester. So if you look, I'll leave this on the screen. And then let's actually take a break for a couple minutes. Because my arm hurts. I'm not used to it. It's been like a year and a half since I wrote. I haven't built up my stamina for writing to the board. Let's take a break for a couple minutes because we've got like 40 minutes left. Go over to the bathroom, stretch. I'll lead us in a series of calisthenics. No, I'm not going to do that. Yeah, take a break for a minute. I'll even pause the recording. Okay, so let's go back to actually calculus and think about integrals and stuff. And something you've seen before, I'll just kind of gesture at the screen instead of writing much down here. Right, so if you want to find the area under a curve, so here's our y equals f of x, this blue curve in this picture. And if you want to find the area from A to B, the way to do it is just like put rectangles underneath the graph or somehow, close to the graph somehow and add up the areas of the rectangles, and that's an approximation, right? Now this is kind of the general Riemann sum, which I think I took this picture from the textbook, so it might be an old edition. I don't know if it's figure 5.33 in our current edition, but it turns out you can sort of break up the interval from A to B in as many, like whatever pieces you want. They don't have to all be the same. And then you can pick any point between 2 successive ones and make that the height of the rectangle. That's kind of the most general Riemann sum. It's a little bit complicated to write down in that case. I could actually, maybe it might be instructive to do so. Didn't think of now until just now of actually writing down what that would look like, but let's see what it would look like because it's kind of ugly. Such a funny noise. I'm squeaking. I used to have these giant erasers that would just like erase all the blackboard. And I need to get back to. I haven't gotten my full classroom mojo back. Okay, so yeah, general Riemann sums. You pick, so you have, I guess you have the function y equals f of x on the interval from A to B. This is notation for an interval, like a closed interval. You see this notation, it's just like, this is like less than or equal to x less than or equal to b is what that represents. And you pick all these points in between A and B, these t sub 0, t sub 1. So we tend to call A t sub 0. So pick t sub 0, t sub 1, t sub 2, all the way up through t sub n, which is B. So we're basically breaking the interval up into n pieces, i.e. break interval into n pieces, not necessarily the same width. We'll talk about the more systematic way where we make them all the same width. And then we pick C sub I between what do we call it? Between T sub I and T sub I plus 1. So maybe I should just draw one of these. So here's our, oh wait, am I still sharing? Nope, I didn't stop the share, sorry. Pause the share. Sorry, okay. I think if I pause the share, this will become big again on the screen. So that's why I'm doing that. Okay, so if we have our, y equals f of x, and then a to b, if we pick our, so somewhere along here is t sub 4 and t sub 5. Imagine there's like a lot of these points and A and B are actually farther away. And then we actually pick, C sub 4. You can see that. C sub 4 between T sub 4 and T sub 5. It could be very close to one or the other. Actually, to be frank, I really should say, something like this. T sub I less than or equal to C sub I less than or equal to T sub I plus 1. Just making things a little more formal. So then what you have is you plug this point into the function and it gives you this height, right? And then you make a rectangle. It's kind of, you can see it in that picture too. You can make a rectangle from this height and this base. So the area of this, it's base times height, right? The height is f of C4, and the base is T5 minus T4. Do you guys believe that? I'm just plugging the point into the function. I'm probably doing the backwards thing of what I should do, which is I'm starting abstract and then we're going to do concrete, but I just want to sort of see how abstract we can be. And then, so that's a rectangle, right? And this is like, height times base. Height times base. And so the area under the curve is approximately, so the area under the curve is approximately the sum, I think I'm going to say from 0. I think the first point would be called C sub 0 because it would be between T sub 0 and T sub 1. So the sum I feel like, well, whatever. Let's say 0. 0 to n minus 1 of f of C sub I times T sub I plus 1 minus T sub I. So that's like adding up all the rectangles. This was one specific one when I was 4. But if I want to generalize, I'm just generalizing this expression here. This is not something you're ever gonna need to do. I'm not gonna make you do this. I'm just trying to like write down something, a purely abstract expression for approximating an area under a curve. Okay. So this is like the fully general Riemann sum. But if we wanted to do, so I think on the screen or on the page, I say, let's do this a little more systematically. Let's actually make all the rectangles the same width. And then also pick the point we're gonna plug in systematically. Like a lot of times we make it the left endpoint of the interval, or the right endpoint of the interval, or the center of the interval, something like that. Right, you could do this abstractly, and the more rectangles you pick, the better it'll be an approximation. But in practice, when we want to make a computer estimate these areas, we better give it something systematic. Right, it's not going to randomly choose a bunch of points and then randomly choose a bunch of, it's not going to randomly choose all these t's to break the interval up into and then randomly choose all these c's. I mean, you could force a computer to do that, I suppose, with pseudo-random generator things, but computers really like order. So more systematic. So what did I say? All rectangles the same width. And we usually call this something like delta t or delta x, depending on however we're referring to the horizontal axis. So delta t in this case is, t sub I plus 1 minus t sub I, right? And then pick all the c sub I is the same, like either the left endpoint or the right endpoint. Yeah, you can sort of see it up there. And then pick all the c sub i's, which are the points that we're plugging into the function to get the heights. Pick all the c sub i's the same way. For example, the left endpoint. So in that case, c sub I would just equal t sub I. Right, that's just like, I would just be choosing the point over here, like on the left side. Okay. That's just, for example, you could do other things. So to go towards more concrete, here's an example. Y equals x squared on the interval from 2 to 6. Okay. And so if we're going to do this systematically, we can actually write this down in a pretty nice way now. You might start to think about how you would write this, like look at number 6, problem 6 and 7. If you want to try to do those, kind of start doing those on your own or with your neighbors. While I erase. You're all just sitting and staring at me, or are you guys actually trying? You're looking down at your papers. Trying this, it's good. Yeah, the area. With 8 equally wide rectangles. And choosing the left endpoint. Yeah, so that's choosing the left endpoint to generate the height of the rectangle. Does that make sense what I'm saying? Another way you can say this is the way I said it here, like the top left of each rectangle is touching the graph. So using left endpoint of each subinterval. A lot of words. I actually think this is part of my thing when I told you about my philosophy with the exams and stuff, is to actually write things out in words and sentences. Of course, when I do on the board, it's a little bit slow and painful, but generate the height. But it's sort of worth it for yourself to write things out in your own words of each rectangle. Right? That's sort of a description of what we're going to do. And that's a description of that picture. In fact, I can probably make that picture bigger. There you go. Let me just show it briefly on the screen for whoever's zooming later. The abstract student who's, for the hypothetical student who's rewatching this later. Right, does that make sense? Does this picture agree with that written explanation? Okay. So then how do we actually write down, you can actually write this. Right, so what's the width of each rectangle? It's actually pretty, I make it work out nicely, right? It's one, is it 1/2? From 2 to 6 is width 4, and there's 8 rectangles, so each one's 1/2. Yeah, so instead of drawing the whole picture up there, what I might do is just draw the number line, like the x-axis, and say here's 2, here's 6, and I want 8 equal intervals, right? So something like that. Probably picked 8 because it was something I could draw halfway decently. And so, right, so this is halfway in between. This is 4, that's 5, that's 3. So this is 2.5, 3.5, 4.5, 5.5, right? And so if you kind of want to write down the abstract thing up there, this is T sub 0, T sub 1, T sub 2, T sub 3, T sub 4, T sub 5, T sub 6, T sub 7, and T sub 8. You can sort of see why it's nice to start counting from 0, because there's 8 rectangles and I end up at T sub 8. There's actually 9 points, right? Okay. And then this is also going to be like C sub 0 and C sub 1. That being the point we're going to plug into the function, all the way up to C sub 7. And then we're not going to need this one if we're going to be building from the left-hand side, right? And then like any of these differences, so the thing is like delta T, right? Delta T is, one way to say it is I just take the width, it's the width of the interval divided by the number of rectangles. Again, words, not a bad thing. So in this case, it's 6 minus 2 over 8, which is 4 over 8, which is 0.5, right? And then if you wanted to start actually doing, so here I said you could actually write out, well, so the number of these rectangles, and I said number of the rectangles from 0 to 7. That's because we're using T sub 0 through T sub 7 to generate our heights of our rectangles. So that's why I said number them from 0 to 7. So like the 0th rectangle, I mean, you could do this very systematically. When I teach like 1700 and I really make students do this really systematically, I do it sort of faster for you guys, but I kind of make them go through and write all these out. So the base is 0.5 and the height is 2 squared, right? Just plug in the left-hand point. And then the first rectangle, which is really the second rectangle, The base is 0.5. And the height is what? What am I going to plug in? Up there. What am I going to, for this, the second rectangle? I'm labeling the second rectangle 1. Yeah. It's 2.5 squared, right? Like, this is the number we're plugging in right here to generate a rectangle. This is the number we're plugging in here to generate a rectangle like that. So 2.5 squared and et cetera. And so you could write this all out in, you know, as a sum of 8 terms. I feel like I fill up the board really quickly. Guess I was writing a lot of English words. Okay, so the next thing you want to do maybe is think about how to write this all out and convert it to a summation notation. That would probably be the next. Yeah, rewrite this in summation. So again, while I'm erasing, start thinking about writing out that entire sum, what the last term is, and how you would actually put that in summation notation. Okay, so the area is approximately 2 squared times 0.5. That's height times base, plus 2.5 squared times 0.5. What's the next height going to be? 3 squared. Not sure why I put the 2 inside or outside the parentheses. I guess if I'm trying to do height times base, I should put it inside. Plus 3.5 squared. Oh. I'm gonna write all 8 terms. 8 is the very edge of what? Yes, we are. A lot of mathematics comes down to just be willing to write stuff down like painstakingly. So never stop it, like I said before. Wait, am I doing this right? Oh yeah, we're ending at 6, right? 5 squared. 0.5 plus 5.5 squared times 0.5. And notice we don't actually use the 6 like in that picture. The 6 doesn't contribute to the height, or the 6 squared. Okay, now how do we put this in summation notation is the question. And here's where I said before, it might be useful to actually label these either index, like I called this the 0th rectangle, this the first rectangle. Because you want some formula that works in terms of I. Anybody see where this is going? So this is the sum from 0 to 7. I'll do the easy part. It's something squared times 0.5. Did the easy part for you. But I want some formula in terms of I. And if you think about it, it's this number, right? So when I plug in 0, I want to get 2. When I plug in 1, I want to get 2.5. When I plug in 2, I want to get 3. When I plug in 3, I want to get 3.5 all the way down to when I plug in 7, I want to get 5.5. Yeah, you think you know? 2 plus 1/2 I. Does that make sense? 2 plus, say 0.5 I. If I plug in I equals 0, we just get 2. If I plug in I equals 1, we get 2.5. If I plug in I equals 2, we get 3. That actually works, right? And it's because we're basically adding 0.5 to the input each time. So it's almost like that pattern we had in the numerators of that problem with the adding 6 each time. Here we're just adding 0.5 each time. Does that make sense? And that's because we're moving from each rectangle to the next, we're just moving by delta t, we're just moving over. So that's right, so that's the Riemann sum. This is a left Riemann sum because we're using the left side of each interval with n equals 8 rectangles. That's officially called. Okay, in general, you can even write this down in general in terms of the t's and stuff. Like, if I wanted to convert this back to in terms of letters, what are we really doing? Well, here's what we're doing. If we break up into n rectangles, we're going up to n minus 1, right? N is 8 here, so that's 7. We're starting at 2, which is the left endpoint of the interval. That's A. And what are we adding? We're adding I times delta t. And then we're plugging that into the function, whatever the function is. Here, it's the squaring function. And then we're multiplying that by delta t. I just completely generalized from one example, but which is not always the best thing to do. But yeah, in general here, if we have, let me just draw this number line again. So sorry, this right here is a general left sum. So you can sort of see this if I draw a number line and I have A and B, and that's T sub 0. Well, what's T sub 1? This is delta T, right? This is delta T. That's delta T. So you can actually see that like T sub 0 is A, T sub 1 is A plus delta T, T sub 2 is A plus 2 delta T, T sub 3 is A plus 3 delta T. And then you see the pattern, right? Notice that this subscript right here matches this number right here. I could even write A plus 0 delta T and A plus 1 delta T. I wanted to make the pattern. Yeah, please.
On the notation for the example, can you remind me why you used between 0 to 7 and actually 6?
Yeah. Or from, oh, not from 2 to 6. Yeah, so that's the thing is the 2 and the 6 are kind of random points, but we want to label them in a systematic way. And so the points that we really wanted were 2, 2.53, 3.54, 4.55, and 5.5. And so we're really counting rectangles instead of it, like, even if I changed in the picture from 2 to 6, if I changed it from 0 to 5 or -3 to 3 or whatever with 8 rectangles, I still want the same sort of sum and the same sort of labeling. So it doesn't really matter the points I started with. It's more like count, like the I is counting rectangles, not counting place where you are on the number line. This formula tells you where you are in the number line in terms of the rectangle number. It's a good question because lots of students, like if I give a question like this on a test, like set up a Riemann sum, a lot of students want to say like I equals 2 to 6. And so it does happen a lot. So that's good. So it's a subtle point. It's that like this index actually counts rectangles. So the index, on time, the index counts rectangles. The formula here sort of finds the rectangles, finds the rectangles on the number line. that's a vague thing to write, but I did want to give you sort of the general left Riemann sum. Is that like this is a totally general formula. That if you, like in our example, if you know the function is the squaring function, that's what f is. You're just going to turn the f into a superscript 2. We know a is 2. We know delta t is 0.5. And that gives us back exactly this. Does that make sense? Very similarly, there's a right Riemann sum. And what's nice is the way we've set it up, the only difference is instead of going from 0 to n minus 1, you go from 1 to n. Because you're just counting rectangles in a different way. Just saying this because we're running out of time. I'm starting to be slightly. Sorry, so the right Riemann sum, using the right endpoint of each interval. Just change the sum 0 to n minus 1 into the sum from 1 to n. Because if you think about if you did the right Riemann sum, so I'd have to draw a whole nother picture, but let me just draw it quickly here. If anybody at home could see this, but so that would look something like using the right endpoint instead, and these would peak over the graph instead of be under the graph, right? That's not 8 rectangles, but you get the idea. And so if you think about it, it would just change these numbers up here. They would start at 2.5 instead of 2, and they would end at 6 instead of 5.5. So it's kind of just shifting everything over. And that's why, so this would just be from 1 to 8 instead. And in general, from 1 to n. Okay. So that's, but it's nice to see the whole like general formula. See how we extrapolate and see the pattern. That's a plus and that's a T. Hopefully that's, I'm writing these nicely enough that you can tell the difference. Okay, so I think I will save. So you could, okay, so the rest of this handout, well, I think what if you had 1,000 rectangles? I guess maybe there's a general point I'll make, and I'll table some of this till next class, but let me just say it in words now, and then we can do it more systematically next time. I could write down this sum. This is a sum. I could change this to a general sum in n rectangles. And then if I wanted, and then that's an approximation for the area. The bigger and bigger I make n, the more and more rectangles I take. If you want to find the exact area, you have to take a limit as n goes to infinity. And all of a sudden, this becomes a much harder problem to like you can have a computer estimate the area with this pretty easily. You can even do it by hand, reasonably. 1,000 rectangles, you wouldn't want to do it by hand, but you could have a computer do it. And you would start to get a sense of what the area is going to be, but it would still be an estimate. If you want to know the exact area, you'd have to take a limit as n goes to infinity of some sum like this. And it's really a painful process, but it's not impossible. And in fact, I claim you can use these formulas and do it. It might be a kind of a fun thing to try if you want. You feel like trying something fun and ridiculous between now and Wednesday, or come to office hours and ask me. I'm probably not going to go through it because it's painful and it's demoralizing. But the point, the very big point, is that we don't ever have to do that because we have this magical thing called the fundamental theorem of calculus. That if we want to find the area under this graph from 2 to 6, we don't actually build the rectangles and do all this. We do this crazy thing where we anti-differentiate, plug in the endpoints, and subtract. And that gives us the answer. And so sometimes I like to hit that, which is like the magic of the fundamental theorem of calculus. That if you were going to actually find these exact areas, you would end up with these horrible sums that you have to then make the top larger and larger until it becomes an infinite sum. And that makes the delta t smaller and smaller. And it gets really crazy to try to evaluate them. And some simple ones we can evaluate if you do enough algebra trickery. And harder ones are just become impossible to evaluate. And again, the fundamental theorem of calculus is magic. So that's what I'm gonna start with next time. So, all right. Great. Let's call it a day. I know it's a minute or two early, but let's do it.